All right, thank you guys for coming. This is a presentation on syntax augmented machine translation, and be discussing two general topics. Focus on the first one, which is challenges in search, and learning effective syntax, which will be a little bit more about how we expect to extend the system. So brief, a little bit of introduction as to what we're generally trying to do with probabilistic synchronous context-free grammars for machine translation. A little bit of motivation as to why we think this is the right way to do it. We'll then talk about two-pass decoding with these kinds of grammars, and we try to address some of the challenges that we face. And a couple of results in syntax augmented NP, some that are actually being generated here at Google. And finally, we'll do a little brief section about learning effective syntax, so trying to go beyond the kind of grammars that we've dealt with so far. So very top-level overview, just to make it clear what we're actually doing. We're starting with parallel text, and we're trying to extract a translation model from that we can then use with additional models to translate new sentences. So today's presentation is really going to be focused on two components, primarily the decoding, and that's what the primary part of the presentation is going to be about, and then a little bit about learning more interesting translation models as well. So why are we making this jump from phrase-based translation to syntax-based translation? So phrase-based translation says, let's start off with that corpus and let's extract a translation model that consists of surface form phrase-to-phrase translations, right? And these surface form models, right off the bat, they don't generalize too well. When you've actually learned stuff about specific words involved, when you get other words that have similar meanings or similar context or usage, that generalization just doesn't happen on new test data. And the reordering models for these systems tend to be separated from the actual words and structures involved. So the reordering models tend to say, do the translation and then jumble it up or distort it to try to produce something that seems more fluent. Right? And these models tend to look very locally, or tend to be more about just penalizing reordering as opposed to letting it occur in a structural way. And also, phrase-based systems have this issue where translation cannot always be broken up into contiguous units. So if we want to translate from one language to another, and we don't have contiguous notions of meaning that can fit nicely into a phrase, that correspondence is going to get broken, and we'd like to have something that generalizes that better. So probabilistic synchronous context-free grammars, so probabilistic because we have weights on each one of these rules, synchronous because it represents translation from one language to another, and context-free grammars, and that's coming from the actual grammar form the grammar formalism that we're using. So here's an example of a kind of rule that we could expect. So we have a left-hand side result, and we'll get back to what that's doing in a second. We have a source side, the n, vb, pa, translating to does not and a vb. Right? So what's happening here is that the source sentence, which might have the words n and pa in it, with something in between, something that we call a vb, is being translated into a target sentence. In this case, the n and the pa, their translation is does not, and the vb is being substituted back in. And this whole thing produces another VP that can be used in further compositions of rules of this form, right? And again, all of this has a weight. This is not a rule-based or transfer system where these rules have been created by hand. All of these rules are being learned automatically from corpora. Now, some key points about this. The translation of NPA in this automatically learned rule does not depend on the words in VB. And all VBs can be used inside the structure. And so what we have here is a process where translation is tied intimately with reordering. We're not saying translate first and then jumble later. We're saying translation and reordering happen together, and reordering decisions need to be made in context. So there's a bunch of flavors of these kinds of grammars being used in the literature. And so they have a couple different perspectives. And a lot of those perspectives come from where you started. And so if you believe that in the beginning there were syntax trees, there were parse trees, and that's what the real data is, there are syntax-based approaches, that we call them, that are really tree-driven. And so there's a listing of them there that really try to produce and generate translations that respect syntactic tree structure and implicitly respect the kinds of rules that have been manually created, the kind of data that's been manually created to build parsers. From the other perspective, we say that we don't really care too much about the trees and the process of building syntactic trees, but rather we want to focus on trees to just augment the process of translation, to maybe constrain it in some ways, but in very limited ways. And what we really trust are the things that have worked well in machine translation, which are learning word-to-word alignments automatically from large corpora, learning phrase-to-phrase associations, and then generalizing them. Right? And there's a whole set of work that follows this line. And what's important to note is that this work typically doesn't get restricted by target language tree structure or even source language tree structure. We simply try to extend what's worked, which are the phrase-based systems. So if we want to add all this functionality, we have to pay the syntax. And the syntax is the cost for actually introducing this kind of modeling into our system. And so we have a couple of basic problems that we have to solve. We have to make sure that we can decode efficiently. And one additional problem is that when we don't have syntactic parse trees available, we still want to be able to represent this kind of richness and maybe learn these labels from somewhere. Right? So the first problem, how do we decode efficiently, is going to actually be the bulk of this talk. The decoding process from the form of the rule, you can sort of imagine a bottom-up CYK parsing, right? And where the goal is to find the most likely translation per span, compose these spans together, and produce a full sentence translation. And what complicates this is the use of an Ngram language model. The minute you introduce the Ngram language model, this decision about simple bottom-up parsing sort of falls apart because you've introduced a model that introduces dependencies across spans, right? So that's sort of the focus of our discussion today. So let's just give a quick example of decoding with these kinds of grammars if the Ngram language model wasn't involved. So we have a source sentence, il ne va pas, and we have some bank of rules that we've learned automatically from corpora, and we perform translation. So in this case, the source word va is being translated to go, and the source word is being replaced with VB, right? And that says now what we've done is we've actually translated not directly from source to target, but from source to some intermediate symbols that are associated with the target symbols, right? So now we can apply additional rules. Now we see ne VB pa. If we have a rule that matches that, like this one, this can be applied on top of it, right? And we keep going and we apply this final rule. And this just an important point here. This is just one possible derivations. What a decoder actually needs to do is to search through the space of all possible derivations using all the rules that we've learned automatically from our corpora, some of which may be noisy, some of which may be good. And it has to do the search to find the most likely translation based on the weights we've assigned for these rules. Right? Now, when we introduce an Ngram language model, this simple search space, this simple Viterbi search that we did through this to translate the source sentence to the target sentence becomes a little bit more complicated. Right? So the Ngram language model introduces dependencies on adjoining regions in the parsing process. Right? So it says that so in the traditional parsing Viterbi search, if you find the translation for a span, you can make a comparable decision. You can throw away all alternative chart items for that span if they have lower cost. But in this case, we can't do that because this Ngram language model introduced dependencies next to the items. So the theoretical runtime of introducing this Ngram language model gets really hairy real fast. Right? So we have the basic s cubed, where s is the length of the source sentence. We have the basic s cubed for the chart-based decoding, but then we have this huge grammar constant sitting out on the side. Right? And there's a couple of important terms that's based on. One is the maximum number of non-terminal symbols that could be in there, and that could be in each rule, and also the order of the Ngram language model, as well as the number of non-terminals we'd like to represent. And in some of our work, we've actually tried to build systems that involve using a very large number of non-terminal symbols. So 38,000 non-terminal symbols, and using Ngram language models of 3 and higher. So what happens? What's the real problem here? So when we actually do the decoding with an Ngram language model, we have this additional model that's trying to say what's the probability of the target word you translated given its left context. Right? Which, as you're doing decoding, you actually don't know the left context, right? Because you're doing a bottom-up parsing approach. So in this case, we're going to focus on one particular path. The decoder, in reality, has to focus on all paths and compare them all together. But we're going to focus on just one. We're going to see what happens. So in this case, the va translates to go or goes or going, several alternatives, and produces a VB. Right? So in that cell that represents a translation of just va, of the source word va, we have 3 alternatives. Right? Now, we can't throw any of them away, even though they all produce a VB, because we don't know how that go, goes, or going is going to combine from the language model perspective to the rest of the sentence. And so as we go up to the next level, we have to propagate these information, right? With this information, we have to keep remembering that these are three separate hypotheses that cannot be thrown away, right? And so we propagate that up to the next level. Let's say we have a couple of different alternatives for the ne pas translation, does not or no. Yep.
I'm sorry, but why would you be able to throw them away if you didn't have the trigram there?
So if we didn't have a trigram language model, right?
Right. Why can't you throw away one of those?
So we would just want to find the most likely translation, right? As long as we just want to find the most likely translation for a particular span, right? Then they all produce a VB, right? And so therefore they're comparable.
So that has to do with the Markov assumption in the CFG.
Exactly.
I see.
Right? So we go up to the next level, and now we have to keep some of these around. And then now we have to keep even more of them around when we get to the very top of the sentence, right? And this was just one derivation. So the Viterbi's chart structure, in this case, for each cell ij, where the cell ij represents I being the number of words translated in the source, and j representing where it's starting, we have these coarse-grained bins for each of the left-hand side non-terminals, right? So the NP or the VB stuff that we saw. And for each of those, we have equivalence classes, where hypotheses are being equivalence classed based on the left and right context. And each equivalence class may contain many chart items. So when we actually have to form a real chart item based on a rule and completed hypotheses and completed equivalence classes underneath, you can sort of see how the number of chart items really grows, right? So for applying this complex rule with three non-terminals, within each of those non-terminals, we have these equivalence classes, right? And so we have to, for each of these equivalence classes, we have to consider how they might combine with all the alternatives from the other equivalence classes, right? So, and for each of these, we need to compute language model costs. And we have to make this decision, and potentially we might even have to make some decisions about throwing some of them away simply to make sure that the search finishes in time. And so we might actually have to approximate the left and right context when making these decisions, right? Because again, this is all happening for one particular chart span. What QPruning, introduced by Chiang in 2005 and 2007, says instead of generating all of these different hypotheses, let's rank them approximately and only generate the first k, right? So we maintain an ordered set of equivalence classes in each of those, for each of those three non-terminal spots, and only generate the first k out of them, right? Now, so this is not an exact first k because we don't know how the language model interaction between alternatives causes the ranking not to be monotone, right? So this is just an approximate first k, but the hope here is that the best translations of the sentence are not going to require really poor translations going further down, right? And so the causes of search error for QPruning are the fact that when you select just this first k, whole equivalence classes are pruned away. You don't even consider whole equivalence classes that are lower down in each of these non-terminal symbols. And you make this decision using left and right boundary costs that are approximate, right? Because we make this decision for a particular cell without knowing how it's going to interact with the rest of the sentence. So what we suggest is let's go one step further with this assumption that we only need to consider the first k. We propose a two-pass decoding approach, where in the first pass, we only propagate the first best hypotheses. And what this means is, in this example here, instead of considering everything from XNP, everything from XPP, everything from XVP, we only consider the first best from each one. And we only propagate this first best up the chart. We leave all the other alternatives there. We don't throw them away. We leave them in there, but we only propagate the first one. And so our new first pass runtime dramatically drops, right? Now, by the time we get through to the top of the sentence, now what we have, because we've retained all the other alternatives, is we have a hypergraph of translations, right? A hypergraph that we can now research. But now we know that we're only going to be searching within translations that we know span the whole sentence effectively, right? So we have translated the whole sentence approximately, and now our goal is to go back and look at all the alternatives that we represented during the first pass search. But what we also do is we try to make this search, the second pass search, in a structured way to allow the direct integration of a left-to-right Ngram language model, right? And in this case, and so what we've achieved is we've been able to limit the language model calculations to only the successful decoding derivations, those that do translate the whole sentence. And now we want to guide our search through the alternatives with the Ngram language model. There's alternative approaches to this. There's alternative and complementary approaches to this. So course-defined parsing uses a similar paradigm where you start off with a simpler grammar. And once you do translation with a simple grammar, you come back and use that as a backbone to restrict additional search. And there's also, Watanabe and I introduced an approach where by making certain strong grammar restrictions on these synchronous CFGs, you can actually simplify your translation search. But these restrictions actually prevent you from being able to model some important reordering patterns. So what actually happens in first pass decoding? Right? So if we look at the same graph that we talked about before, so what actually happens here? So when we look at the va translating to a VB, instead of representing go, goes, and going, all we send up to the next level is the go. And we keep the other two. We'll come back to them later. At the second level, now we have a couple of alternatives. We have does not and no. But now we only have to see how that matches up with the go. Right? And same for the next level. Right? We keep all the other alternatives there, but we only propagate one hypothesis as we go up. So we want to propagate one chart item per cell, the one with the highest weight. That includes the language model costs.
So when you say you include language model cost, you only include language model cost of go, not the other two.
Not the other two. Right? So it's their search errors being made there.
So if you have only one word there, then why do you still need to use language model?
So if I only have just a couple points there. I'm using this goes and going and stuff to represent equivalence classes. Right? In this case, go would be its own equivalence class because it's just one word. But in reality, there would be left and right context for all of these hips. Right?
Okay, and this one, is this equivalent to k equals 1 QPruning? Or?
Yep. But if you do k equals 1 QPruning, in reality, you would throw away all the hypotheses. We actually keep them around. Right? Because we're going to go back through it again. Okay? So the result of this, because we kept all these alternative hypotheses around, is going to result in a hypergraph of alternative sentence spanning parses. And if we just look at the first pass, it's going to be exactly right. It's going to be equals k equals 1 QPruning. But there's going to be significant search errors. Right? And so now the question is, in the second pass, can we recover from these search errors given that we're applying a left to right language model? So what we want to do is we want to explore this sentence spanning hypergraph of derivations in a way that allows the Ngram language model to keep making updates and to really drive the search. Right? We don't want to instantiate the whole hypergraph. That's a very bad idea, right? Because now we have an exponential number of hypotheses. We don't want to evaluate every single one of them. We only want to evaluate a small fraction, and we want to pick that small fraction based on the Ngram language model. And if we structure our search in a certain way, we can actually introduce high-order language models into the search process, right? And this is going to be significantly better than just doing rescoring alone. So how are we going to do this? We're going to start off with a sentence-spanning hypergraph at the very top there, this underscore s that has a weight, right? I use underscore s to represent that it translates the whole sentence. And we're going to look at the first alternative in there. So let's say we have this 3 non-terminal rule, this NP2, VP3, PP. That has a weight, right? Now we look a little further and we say, can I find any alternatives if I use the second best alternative for the NP2? Right? So when I use the alternatives for NP2, we have to do a couple things. So let's say the first best was the nice dude. That was the first alternative in NP2, and that's the one we actually found during search because we were looking at first best for everything. But inside NP2, there was an alternative that we didn't consider. There's a grayed out one, the kind man. So what we'd like to do is we'd like to find out the weight of this alternative hypothesis. And so the questions are, how can we officially calculate W2 when W includes both the rule weights and language model probabilities? And W also includes language model estimates that have been made during this first pass. We want to do this by making the least calls to the Ngram language model. Now, one critical point here is W2 let's say we're dealing in cost space, W2 could actually be a lower cost hypothesis than W1. Right? So now what we're doing is, this is the whole goal. We know we've made errors in the first pass. Now we want to come back and correct them. So what do? We maintain a sentence-spanning beam of trees that we're always partially expanding at the left. Right? And so when we calculate this alternative weight, all we have to do is we have to divide out the language model probabilities that came from using the nice dude and factor back in the alternatives that came from the nice man. And in practice, this is not going to be too bad because we don't have to recompute the language model probabilities for the whole sentence, but just up to the first non-terminal. Right? In practice, it could even be up to the second non-terminal, but we simply go up to the first place where we need to keep tracking. Right? So if these non-terminals are very small, you could potentially have to bridge one, but it's a constant factor. Right? So we factor out the estimates that we made and factor back in these alternatives. Right? And we do this until the full context has been considered. Okay? Now when we do this second pass, we actually find some interesting things, right? If we expanded VP3 to gave me, right, that's one of the alternatives in there, we actually now produce the nice dude gave me and some non-terminals, and a kind man gave me and some non-terminals. Just like in phrase-based decoding, we can actually recombine these two hypotheses, right? Because at this point, we know the right context of this hypothesis is only gave me. And if one's better than the other, we can throw the worst one away because we know that it can't suddenly have a great language model probability. Right? And so we can do language model recombination through this process as well. So how do we measure the impact? We've proposed a different decoding algorithm, and now the question is, how can we actually evaluate this? Is it faster? Right? Now, and we'd like to do this by looking at what components of the search really take time and see if we've reduced that. Now, this two-stage search easily outperforms a naive method, which is simply saying, forget the language model during the first pass and just use it to rescore the n-best hypotheses. Right? QPruning should be the baseline that we compare against, right? So the alternative single pass approach that is basically saying, let me explore up to k at each step. And how do we do this? What we want to do is we want to evaluate a couple things. How many times are we asking for novel language model probabilities from the language model? And compare that versus model cost. Right? Model cost is a representation of search error. The lower the model cost is, that means we've found, according to our model, we found a better translation. And what we don't want is to leave good translations on the table and walk away from them. Right? And so what we'd like to do is we would like to keep searching and searching and searching until we found an acceptable model cost that will produce a good translation. How do we measure model cost? We simply measure the cost of all the first best hypotheses on a test corpus. Lower cost implies lower search errors. And the reason why we measure against language model cache misses are these are the expensive ones. Right? So how are we going to evaluate this? We're going to evaluate this on it's a reasonably small corpora, but this is sort of the resource constraints that we had when we were doing these experiments. It's a Chinese to English translation task, about 120,000 parallel sentences. And we evaluate a couple systems. We evaluate our hierarchical system as well as our syntax-based system. Can I have a quick time check?
It is 11:27.
Great, thank you. So we evaluate two systems. One is a purely hierarchical system where the grammar has only one non-terminal in it, and a syntactic system where the grammar has a large number of non-terminals in it. And we'd like to see how the two systems differ in the way they behave in these two decoding approaches. So here are the results. The graph on the left is the hierarchical system. The graph on the right is the syntax-based system. Now, what does this curve represent? Right? So the different points on the curve represent selecting different values of pruning during decoding. Right? Selecting tighter beams during decoding lead to larger search errors, so larger model cost. And selecting looser beams lead to lower model cost. Right? And so the goal that we're trying to evaluate is to see which decoding approach can get to the lowest cost faster. Right? which decoding approach can really do a good job of exploring the search space quickly and get us to a low model cost. Right? And what I've also annotated along the way at each point, so these different points again are different pruning levels, I've also annotated the blue scores that are associated with these points. Right? And this is primarily for just an understanding of how well the blue score correlates to our models, but the blue score is the automatic evaluation metric for machine translation that's not based on our models. It simply is trying to compare translation you output versus some reference translations. And so what we see here is we see these two systems, and we're evaluating the number of language model cache misses. So we're saying which system with fewest cache misses can get to a low model cost. Right? And so in the hierarchical system, we see that the heuristic search, which is what our two-pass approach system is reaching the model costs more quickly for most of this curve than the QPruning system, right? And it's a similar picture for the syntax-based system, right? We quickly achieve the model cost. Now, a couple of interesting things are going on here. One is with the syntax-based system, the blue scores annotated at each of these points doesn't seem to change much, right? So as we search more and more and more, we don't really see too much of an improvement in blue score. But for the hierarchical system, as we search more and more and more, as we make wider and wider beams, we see this pretty steady improvement. We see a pretty steady improvement that shows that as you search more, as you find alternative language model combinations of different hypotheses, your score is actually going up. Whereas for the syntax-based system, you very quickly achieve a higher score, in this case in the hierarchical system, but searching for more and more language model alternatives doesn't seem to help so much. There's a couple of different interpretations. There's the interpretation that favors the use of syntax, which says, well, the syntax is providing a good syntactic structure, trying to produce fluent translations, and that's why searching for more and more language model alternatives is sort of unnecessary. The syntax is doing that for us. That's a very optimistic way to look at it. A more practical way to look at it is there might be some of that going on, but there might be also the fact that the syntax-based system has a much larger search space. And we could be still at the tip of the iceberg here.
I'm sorry, can you please go back to the previous slide?
Yeah.
You mentioned that the significance level is 0.8 blue score. What does that mean?
So if there are methods to try to evaluate the significance level. So when is the system really different from another system? Right, and it's done by sampling, right? So you sample the range of blue scores that you can get if you change your data set. And so it's about 0.78. So the idea here is if you say one system is really better than another system, if it's got 0.78 difference. But there's a lot of controversy as to whether that's a valid thing to evaluate.
Then the differences that you have there, are they within 0.7?
Yeah. No, they're not within. They're so 19.1 or 0.191 compared to 20.7, that's more than the significance.
So I need to multiply these by 100.
Yeah, so I'm giving the blue
with
score in the way that it's, yeah, right, you're right. Compared to the significance on the previous slide, compared to this, you should multiply this by 100, right?
So these are significant in fact.
Yes, between the two, right? So syntax
But
versus
on a given
hierarchical.
plot, the changes there may not be significant. Right?
They may not be, but for example, on the language model, on the hierarchical system, across the whole range it is, but for the
From
syntax,
one end to the other.
yeah, from one end to the other, but on the syntax-based system, it's not. Right?
What kind of statistical significance thing is it?
In this case, so this is a confidence interval that's built based on translating different selections of the test set. Right? Another point, just want to make this point at the bottom. We're comparing against the language model misses, because these are the expensive ones. The language model total calls, we make significantly fewer language model total calls. Right? But typically, a system will cache these calls and not have to make them again and again and again. Now, the next thing to evaluate at the end of the day is just raw time, right? So we're the solid line, and the alternative approach is a dotted line. So are we doing it faster? And for some part of the range, we are doing it faster, and for the rest of the range, we don't quite do it as fast. We actually cross the curve, right? So we went into a little bit of analysis as to why this is happening, and it turns out that most of this time is actually spent because the memory access pattern of the second half of the search is actually really poor. Right? So we do a lot of creation of hips, a lot of deleting, a lot of creating, a lot of deleting, and that's what that time is coming from. So we've used these kinds of approaches in a couple different systems, right? So we've applied the syntax-based approach as well as compared against a hierarchical-based system for French to English translation, and we see statistically significant improvements. And currently at Google, we're also running a set of experiments where we've started integrating our system into the Google environment, and we see right now improvements initially with a purely hierarchical grammar, and the syntax-based system is coming. Now, these are the results that are created with a 5-gram bash language model, so we have to sort of re-architect our code a little bit. And the results are definitely still preliminary, right? So these are not solid results yet. So a couple examples, cases where one system is better than the other, right? So this is the kind of tree that we produce in our translation. So it says that at present, the scope of this investigation is gradually narrowing. That's a system that the hierarchical system produces. And a phrase-based system says now it is gradually narrowing the scope of this survey. Right? So slightly different translations. We have alternative cases as well, obviously, cases where the hierarchical system is worse. And in this case, it's pretty significantly worse. So we produced the teacher's eye, suddenly Yishan began quietly celebrating. And the phrase-based systems at least seems to make slightly more sense. So a couple different alternatives and a couple trees to look at. Now we've done all this, the experiments even here have been done with a simple hierarchical grammar, right? And we intend to add phrase structure trees to improve this, to add syntax into the mix. But can we learn these labels without phrase structure trees? Phrase structure trees are created for a totally different purpose. They were not created for translation purposes, right? They were created based on tree banks. They were created based on people that felt like they understood how sentences were created. And they were not created primarily for the purpose of improving translation quality, right? And so a small addendum to this presentation is some current and future work about how we plan to address this problem. So if we don't have phrase structure trees, what can we do? Can we learn labels that actually improve translation quality, right? So we have two examples here. One is we have a sentence with alignments, and we say, we're missing the tree. What can we do, right? And so currently, we can actually just produce X's, and we say that we have a single generic non-terminal that's not labeled. We can produce some decent translations. So we actually propose a extension, a novel formalism, that's based on preferences for hidden labels. Right? So these hidden labels, the supposed syntactic structure behind the sentence, is never actually observed on any trees. But we can talk about them being hidden variables that we'd actually like to learn. Right? And so for each rule, it can prefer for each of its non-terminals, it could have a preference for some hidden non-terminal symbol. Right? And these hidden labels are just indices, just like in clustering. Right? And our goal is to actually say, can we learn such labels discriminatively? And as well as learning these labels discriminatively, can we marginalize them out during decoding? Because at the end of the day, we want to produce good translations as opposed to good labeled tree translations. And so there's significant precedent for using hidden labels in literature to do tasks of this form. And so how does this actually look? Right? So previously, we just had these X's, or these non-terminal symbols, with their name being whatever we call them, whatever we wrote them down as. Right? So now what we say is that X spot, it's not just X. It's X that has a preference for being index 3, which might be NP, of 0.7, and some other weights for all the other potential different options. Right? So each non-terminal gets a preference of weights. And when we calculate the probability of a derivation, we also introduce this preference compatibility. We say, how compatible were the two preferences? If one rule produced something that's of hidden type VP, and the other rule needed something of hidden type VP, then that's a good match. And if it didn't, then that's probably not such a good match, and maybe that's a bad derivation. And so we can actually write a translation model, so we don't have time to go into too much detail here, but it's simply two components. The left component is the traditional probability of a tree derivation, and this additional component that measures how well all these rules that we used join up. Right? If they join really well, it's going to favor a certain derivation. If they join poorly, it's going to downweight that derivation. Once we have this, we can actually take a discriminative approach to maximize the probability of oracle selected trees, so oracle selected based on some automatic evaluation metric. We can maximize this conditional probability, and we can train the parameters of the system. Right? And so we have two kinds of parameters in the system. One is our traditional model costs, and then millions of little features. And these little features are, for each rule, for each non-terminal, there's a preference for being one of a set of hidden labels. Right? And so we can actually easily take the gradient of those features, and we can optimize the system.
So
Yep.
one question here. The oracle tree and
Yeah.
the trees that you consider,
Yep.
they're coming out from completely different data, right? Well, the tree that you consider is from the unlabeled data that you learn from the sentence pairs. But the oracle is from still the linguists who actually annotate.
No, the oracle is simply generic single non-terminal.
But what you said, selected by automatic metric, what do you mean by that?
So I say use a simple grammar to translate a sentence and generate its n-best list. Right? And so now you have n-best trees with a simple grammar. One of them was really good by the blue score.
So it's still selected by blue score?
Absolutely.
Not like
Yeah.
any parse tree? Or
No. That oracle is by blue score, right? So that's the whole thing we want to introduce. We want to pick labels that produce good translations, not produce good linguists, right? Okay, so it's a simple estimation procedure that I just actually described to you. We extract a simple grammar. We train the monolithic model parameters on some development corpus, and then we translate some other corpus, right? We iteratively translate that other corpus to produce n-best lists, let oracle selector, which in this case is an automatic evaluation metric, pick good translations, and run this optimization. Right? And we can repeat this until no new trees are found during a translation step. And the goal here is that, ideally, good labels are learned that actually explain good translation, right? As opposed to these non-terminal categories. And so the impact of this ideally, it should be able to reduce spurious ambiguity in the grammar, because we actually do get to sum out all of these hidden non-terminals. That's how the model is written. And this formalism generalizes the previous work in the field, which is using a single non-terminal symbol, using these multiple non-terminal symbols from syntax. And it's a discriminative approach. We're really trying to improve translation quality. So general top-level conclusions, I spend the most time talking about this two-pass algorithm that really tries to avoid unnecessary language model calls. And we have some results that demonstrate the value of using these kinds of systems. And a small proposition for a formalism and model to learn labels discriminatively. That's about it.